Hi, our listeners. Here I'll make an introduction about our newest published paper on the flow field classification problems based on quantum annealing algorithm. So first, let me introduce research background. As you see in the title, the paper is about the quantum techniques application in the aerodynamics field. So the reason we chose this topic is real-time identification of the aerodynamics parameters really faces some challenges, and that there are requirements for improving aircraft flight efficiency and prevent a runaway and giving early warnings of structural overload. So traditionally, the aerodynamics parameters are measured by some pressure sensors that attach on the surface of the airfoil. And the defect is that they normally do not provide global flow dynamics for the aircraft. So we hope to bring some suitable algorithm with the introduction of techniques from other fields. Then for our methods, we choose support vector machines for aerodynamics classification problem. And to shortly conclude, the algorithm is that the support vector machine constructs a hyperplane in the data space according to the maximization interval criterion to distinguish the two classes of points as the hyperplane here that distinguish the black dots and white dots on the figure. And the SVM can be described as a convex quadratic optimization problem, which is a QP form, as you can see here. And then we'll introduce our quantum annealing version. The hardware we use in our paper is the Advantage system from D-Wave company. And here our workflow. We first mapping aerodynamics classification problem to a cubal form. Then we have to construct our one against all based multicast classifier. And then we use some like PCA and other data pre-processing techniques to pre-process the data. And then we pull this data into our classifiers and see their performance. Okay, here let's see our detail to construct a quantum annealing-based classifiers. So there are mainly, let's say, two steps. The first is to encode the continuous variables to a binary form. That change the alpha n into the binary variable an like that. And then we have to set a normalization condition C. So after these two steps, we'll result a QB form of the problem. And for our first tag of the paper, the boundary separation detection, the data set is composed of 45 points that are acquired by the sensors of the pressure sensors that are attached on the surface of the airfoil, and 27 points of the data are represented boundary layers that have not separated, while the other 18 points stand for the boundary layer separated. And let's see our result. So the figure demonstrates our result. So A represents the result of the hyperplane of classical classifiers, and B represents the resulting hyperplane of the quantum version classifiers. And according to some different indicators, we can see our quantum annealing-based support vector machines has comparable performance in most indicators, and actually they both have good classification performance. And then for our multi-class classification problem, the angle of attack classification. So there are a total of 106 pressure measurement points, which is acquired by the CFD simulations. And we separate the data set into 20 degree, and we try all these data points and see the performance of different kinds of classifiers. And actually, we find that the angle of attacks are much harder to distinguish after boundary layer separation than before the boundary layer separation. So finally, we choose a dataset of the flow field data after the turn, consisting of data from 14 degree to 20 degree angle of attacks, with 9 data for each angle. So the final result we'll see here is that for different group of data sets, the quantum version SVM have good performance compared to classical SVMs, and the standard deviation is 0.1 to 1 for the classical support vector machine, and 0.0997 for the quantum annealing support vector machine, which means the quantum version SVMs have a relatively higher classification accuracy for the AOA classification task. And in the end, we'll conclude our paper. So the paper introduced the quantum annealing-based support vector machine to the flow of fluid dynamics, and demonstrates that it outperforms classical classifiers in both binary and multi-class classification tasks. And as for the advantage, it stems from the idea that the quantum annealing-based support vector machines return some several near optimal solutions instead of the global optimum, and make it possible to better generalize the distribution of different kinds of points. As you can see in the figure here, for classical SVM, we only have one result that is global optimum, and for quantum SVM, we can have different result of same data set for different repetition of the experiment, and all these results may have some features of the data set and by combining them together, we may have a better classification performance compared to the one single one single result from the classical classifiers. And the use of the data-driven classification methods to detect the flow separation and angle of attack conditions is of great importance for aircraft design and flow control. So the present work can be useful for online flow field classification and control along with other flow field feature extraction methods. So it's very exciting for real-time control of flow field with a wide range of applications. As a and as the computation power of the quantum processors increases, the integration of the quantum computing with various disciplines will become more common, and quantum advantage may be widely realized. So this is all our work about, and thanks for your listening.